in our 12th standard physics class, and in the lesson unit number 3, magnetism and magnetic effects of electric current. This is our session number 16. Today we are going to learn about a new topic, moving coil galvanometer. You might have a question about the term moving coil galvanometer. Let me explain that from now. Moving coil galvanometer. Dear students, the galvanometer is a device used to detect a small electric current or measure its magnitude. The current and its intensity, that means the strength, are usually indicated by a magnetic needle movement or that of a coil in the magnetic field, which is an important part of a galvanometer. Since its discovery in the 1800s, the galvanometer has been much repetition. Some of the different types of galvanometers are tangent galvanometer, astatic galvanometer, mirror galvanometer, ballistic galvanometer, and the moving coil galvanometer, which we are going to learn in this class. Let me first clear your query. What is a moving coil galvanometer? Do you have that question? Yeah. What is a moving coil galvanometer? A moving coil galvanometer is an instrument that is used to measure electric currents. It is a sensitive electromagnetic device that can measure low currents even of the order of a few microamperes. So, what may be the principle of the moving coil galvanometer? Let me first clear the principle. When a current carrying loop is placed in a uniform magnetic field, it experiences a torque. This is the principle of this moving coil galvanometer. Now let's see what are the constructions and what are the things we have for the construction. Let us take a rectangular insulated thin copper coil and let us name the edges as P, Q or S. Here you can see P, Q, R and S. These are the edges of this insulated thin copper coil. This coil contains a large number of turns wound over a light metallic frame. This is a light metallic frame and it has a large number of coils wounded on it. A cylindrical soft iron core is placed proportionally inside the coil, which you can see in the diagram. A moving coil here. The rectangular coil is suspended freely between the two poles pieces of a horseshoe magnet. Horseshoe magnet is here. You can see the horseshoe magnet here. The upper end of the rectangular coil is attached to one end of the fine strip. This upper end of the coil is attached to a fine strip of phosphor bronze. The lower end of the coil is connected to a air spring which is made up of phosphor bronze. In a fine suspension strip, a small plane mirror is attached. It helps to measure the deflection of the coil with the help of a lamp, which we have here, which is connected to the torsion head. The suspension strap and the spring S are connected to the terminals to pass the electric current through the galvanometer. It helps to pass the electric current through the galvanometer. Now let's see the working of this moving coil galvanometer. Here you can see the L be the length of the rectangular coil PQRS and B be the breadth of the rectangular coil PQRS. Here PQ is equal to RS. PQ is equal to RS. That means if the PQ is equal to L and Rs is equal to L. QR is equal to SP, that means which is equal to B, the breadth. Here I the electric current flowing through the rectangular coil PQRS. The sides QR and SP are always parallel to the magnetic field B. The sides PQ and RS are always perpendicular to the magnetic field. The sides PQ and RS are always perpendicular to the magnetic field and it experiences equal forces in opposite direction. The horseshoe magnet has hemispherical magnetic poles which produces a outspread magnetic fields here. Now, due to this outspread field, the sides QR and SP are always parallel to the magnetic field B and they experiences no force. Remember students, for a single turn, the deflecting torque is tau is equal to BF breadth into force, which is equal to small b breadth into BIL, which we know in the last session. That means F is equal to BIL and we take this as LB, we take this L out. So LB, length into breadth, is equal to B into I. And we know length into breadth is equal to area A. BI is equal to, so we put BI is equal to A into B into I. Here I represents the current. Since the area of the coil is equal to A is equal to I into B, L into B. For coil with n turns, I already mentioned you about that number of turns in the coil, it is n number of turns. So we get tau is equal to N A B I. A area, magnetic field, B, and I is for the current. Later, the moment of restoring torque is proportional to the amount of twist theta. Therefore, tau is equal to K into theta. That means NAB is equal to K. See, due to this deflecting torque, the coil gets twisted and restoring torque, which is also known as the restoring couple, is developed. Later, the moment of the restoring torque is proportional to the amount of twist, that means the theta. That's why we put theta, the K is equal to tau. You can see here, tau is equal to K into theta. The K is the restoring couple per unit twist. K is the restoring couple per unit twist. See, at equilibrium, you know what is the position meant for the equilibrium. The deflecting couple must be equal to the restoring couple. The deflecting couple is equal to the restoring couple. Restoring means regained couple force. From this coils, it has a regained couple of forces. Therefore, already we know, instead of tau we put NABI, and which is equal to K into theta. So if you take I here and take the NAB, which is down of K theta divided by NAB, inverse value, then let we have I is equal to G theta. That means K KNAB is equal to G. KNAB is equal to G. We substitute G instead of this KNAB. G is equal to KNAB. And this G is called the galvanometer constant or current reduction factor of the galvanometer. Dear students, since the suspended moving coil galvanometer is very sensitive, we have to handle with eye care while doing the experiments. Most of the galvanometer we use is a pointer type moving coil galvanometer. On behalf of that, let's find the figure of merit of a galvanometer. It is defined as the current required producing a deflection of one scale division in the galvanometer. The figure of merit of a galvanometer is defined as the current required to produce a deflection of one scale division in the galvanometer, which we saw the scale which is in the galvanometer construction. Then the sensitivity of the galvanometer. The galvanometer is said to be sensitive if it shows large scale deflection even for a small current passed through it or a small voltage applied across it. Next one, current sensitivity. Current sensitivity is defined as the deflection produced per unit current flowing through a galvanometer. It is defined as deflection produced per unit current flowing through a galvanometer, which is 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 equal to, that means the current sensitivity is equal to theta by I. Already we know the value of I from the equation we got. I is equal to K divided by NAB theta. So while substituting the value of I here, K is divided by NAB theta, we can cancel this theta here and the theta here. So we can put IS is equal to NAB by K. We can cut this both theta. So we take this NAB in the upper hand. So NAB divided by K. Already we know G is equal to K by NAB. Is it? G is equal to K by NAB from the equation we got in the moving coil galvanometer. Finally, we can substitute that IS is equal to 1 by G. That means instead of all this, you can put G and it is an inverse one. So 1 by G, and which is equal to IS is equal to 1 by G. Methods to increase the current sensitivity of a galvanometer. This is a 2-mark question and very important 2-mark question. Let me give answer for this. The current sensitivity of a galvanometer can be increased by increasing the number of turns N, increasing the magnetic induction B, increasing the area of the coil A, and decreasing the couple per unit twist of the suspension wire K. These are the methods to increase the current sensitivity of a galvanometer. The phosphor bronze wire is used as suspension wire because the couple per unit twist is very small. That's why we use this phosphor bronze wire in the upper end and the lower end of the moving coil galvanometer. Next one, voltage sensitivity. It is defined as the deflection produced per unit voltage applied across the galvanometer. We know Vs is equal to theta by V. As we got in IS, Vs is equal to theta by V. And Vs is equal to theta into I into Rg. So already we know I is equal to K into NAB into theta, is it? So we can substitute the value of I in this term. If you substitute the value of I here, then Vs is equal to NAB divided by KRG. Already we also know that capital G is equal to K by NAB. While substituting the value of capital G here in Vs is equal to NAB by KRG, we get Vs is equal to voltage sensitivity is equal to 1 by G capital into R small g, or instead of 1 by G, instead of this 1 by G, you can put Is, is it? That's what we got from the current sensitivity. So Is divided by Rg, Vs is equal to Is divided by Rg, because we know Is is equal to 1 by G. Rj is the resistance of the galvanometer. Here the small g represents the galvanometer. Thank you students. See you in the next class.